All right, we're back. We're on notes 28, Calc AB, page 2. We're going to keep rolling. So we're doing L'Hopital's rule. We're looking at weird cases, right? Not strictly 0 over 0, infinity over infinity, things that we have to manipulate to become 0 over 0 and infinity over infinity. If you just finished watching the first video, we did an example at the end of that. This is going to be essentially the same thing. It's really the same process every time. So you look at it, you decide, is this something I should be trying to use L'Hopital's on? So this 1 over x goes to 0. So this is kind of a 1, I don't have a pen, a 1 to the infinity situation. If there's an issue that involves an exponent, then the technique you're going to use is pretty much always to take the natural log. So we want to define a function that we can take the natural log of. So we'll say it's 1 plus 1 over x to the x. Now let's take the natural log. That was the whole point of doing it. Natural log of y equals, I'm just going to bring the exponent down. It's the natural log of the thing to the x, so it should become x times the natural log of the thing. So x natural log of 1 plus 1 over x. So we have this. Now our goal here is really to take the limit. So we want, if these things are equal, then their limits are equal. So if I take the limit as x approaches infinity, so sometimes I'll skip this step and I'll immediately put the limit inside. That's between you and kind of your teacher, I guess. There's other techniques that you can use for this. I prefer to do it this way. I think that it'll work every time. I'm familiar with it. So this will be x natural log of 1 plus 1 over x. Okay. So the whole idea now is that you basically ignore the left-hand side and you just work on the right-hand side. So let's work on the right-hand side. So we're working on, I guess, we're going to work on this and think about what can happen here. So if x approaches infinity, this will give me infinity times the natural log of 1, and the natural log of 1 is 0. So this is infinity times 0. This is the same scenario that we had at the beginning of these notes. 0 times infinity, you want to invert something and then apply L'Hopital's. So here, I'm going to say this is equal to the limit as x approaches infinity. Which of these would you prefer to invert? It's not really, it's like a question, but like there's really one definitive answer. Nobody wants to invert the natural log thing. That's crazy. But here, okay, so then you check. Is this equivalent algebraically to the previous step? It definitely is, right? Simplify the complex fraction, you're back to the original. So it's a valid thing to do. You changed the way it looked, you didn't change what it is. That's like a really common thing to do. Now if we try to do this, we'll actually get 0 over 0. This is a L'Hopital's situation, finally. All right, not only is it a L'Hopital's situation, but it's like the best kind of L'Hopital's where the chain rule is going to knock out the derivative of the bottom. So that happens like way more than you would expect. So let's L'Hopital's this. Let's make it clear that we're using L'Hopital's. L'Hopital's. You know what's interesting? On the AP exam, they spelled it as H-O-S-P-I-T-A-L, I think. And I've heard people do that. I've never seen that before, like in print, I think, or I don't read closely enough. Anyway, we're doing it. All right, so don't even bother to simplify this. Just do 1 over 1 plus 1 over x, right? Derivative natural log of something is 1 over that thing times the derivative of that thing. So then times the derivative of 1 plus 1 over x is negative 1 over x squared. That's the magic thing. So the chain rule here really saves you. So here, the derivative of the bottom is negative 1 over x squared. That's great. This thing and this thing will cancel. That happens like almost all the time on these sorts of problems. So this, what would my work look like if I were a good student? You know what I'm gonna do? I'm gonna copy, this is my game plan. I'm gonna copy this, and I'm gonna copy like this whole step. And I'm gonna rewrite a new step, and I'll say therefore, because when you want your work to go from sloppy to neater, if you say therefore, it looks a little better. Natural log of y equals the limit as x approaches infinity of just 1 over 1 plus 1 over x. Okay, so if that happens, then I'm going to do the natural log is continuous. I can move the limit inside type of thing. And then I'll actually take this limit, right? So if x goes to infinity, this is 1 over 1 plus 0, so just 1. This is where the trick answer would be 1, and like 50% of people will pick it, and they'll be like, yeah, I got the limit. You didn't. You got the limit of the natural log, right? So then the actual limit as x approaches infinity of y is equal to e to the first. So I'm going to write the whole thing again, because I think that's the good thing to do. Limit as x approaches infinity of 1 plus 1 over x to the x equals e. That's the famous, I think in my mind, that's the most famous definition of e, is this one. Your mileage may vary. I don't know what you prefer. So I prefer, later in your life, you're going to learn Taylor and Maclaurin series and power series and things like that. I prefer the Maclaurin series for E. I think that that is like the best looking thing. And when you get there, I think you will agree with me, but I'm not going to show it to you just yet. You've probably seen it. It's got like, it's the sum of x to the n over n factorial, n goes from 0 to infinity. It's like, it's nice. It's a beautiful math result. All right, can we do this one? Can we do this one quickly? Can I do anything quickly? Tough call. All right, let's just do it. Let's see. How many steps is it okay to skip? Let's say that this is basically, well, I mean, we're dealing with 1 to the infinity again. So I'm going to say that it is the natural log of the limit as x approaches infinity of y equals the limit as x approaches infinity of x natural log of 1 plus r over x. Oh my god, it is so windy that I feel like my windows are gonna like just pop in here. That'll make for a good video. So I regret, I should have said y equals. Can't do anything fast. It's like, I'm not taking the greatest notes, but still I have standards. Okay, so we're basically ignoring the left. We're gonna work on the right. So this is your infinity times 0 situation. I mean, this feels very similar to the last problem, right? Hopefully. 1 plus r over x over 1 over x. This is 0 over 0, and so we can L'Hopital's. So L'Hopital's. All right, and then if we actually do that instead of just say it, we'll get the limit as x approaches infinity of, remember, you don't want to like simplify too much. So this will be 1 over 1 plus r over x times the derivative of 1 plus r over x. So this is a little more complicated because there's that r, but to call this complicated would be an insult to complicated things. So here, and then the derivative of the bottom is negative 1 over x squared. So we still have a canceling situation, but when we cancel, I'm going to highlight something different this time. When we cancel, this r doesn't cancel. It's still there. So this becomes, so let's say, therefore, the natural log of the limit as x approaches infinity of y is going to be the limit as x approaches infinity of, that r is still there. So r over 1 plus r over x. If x approaches infinity, that on the right-hand side actually just approaches r. So we get the natural log of the limit. If I could stop writing that, it would be way faster, but I can't do it. So this becomes r. So the limit as x approaches infinity of y is equal to e to the r. Could you have predicted that going into this problem? I think you could have. There's actually a really clever substitution that you could make that like makes this pop out really fast. But I didn't want to do that. I wanted to actually like go through this process and get this. Should I write the final thing? I guess so. So therefore, the limit as x approaches infinity of 1 plus r over x to the x equals e to the r. So this is what I mean by we've essentially done the same problem 3 times now, with just like minor modifications, but that's okay. All right, let's do this last problem, and then we'll call it a day. All right, what are we dealing with? We're dealing with infinity to the 0. What is that, right? Because it's, first of all, infinity is a concept, not like an actual number. And then it's not actually 0, it's just approaching 0. And how fast is it approaching 0? That will determine like what's going on. So we're going to do our y thing. So y is equal to x to the 1 over x, natural log of y equals, let's say the natural log of x over x, right? Exponents become coefficients. So the natural log of the limit as x approaches infinity of y. I decided to add those parentheses in couple problems back, couple steps ago. Limit as x approaches infinity of natural log of x over x. Okay, so this by relative growth rates is definitely 0. If you don't like that, this is infinity over infinity, so that's a L'Hopital situation. So we can use L'Hopitals. Do we need to? I mean, I guess we need to. I mean, the notes are called L'Hopitals, so I guess that's the idea. So we get this, the limit as x approaches infinity of the derivative natural log of x is 1 over x, all over 1. There you go. This limit, so then we could say the natural log, the limit as x approaches infinity of y is equal to, that limit is 0. Okay, so is the answer 0? No, the answer is not 0. The answer is, well, even this is, well, this is the answer. Just like you gotta, I don't like to leave it at that transitive property at the last step. We get e to the 0. E to the 0 is 1. So the limit as x approaches, what is that? As x approaches infinity of x to the 1 over x is equal to 1. And we got it. Hopefully. Should we check it on a calculator? I mean, I guess so. You should check everything. Like, be suspicious of your work. That's how I live my life. It's like, do I think I got it right? Yeah, I think so. X to the 1 over x, x approaches infinity. You know, I got this, all of a sudden I had this feeling that we were actually supposed to go to 0, but no, like that, we get 1. You know what's really interesting is you can do, this doesn't matter, but I think it's really weird that you can like fill in like from the right. Like, how do you approach infinity from the right? How do you get to the right of infinity? Like, what are we doing here? But anyway, let's go back to the notes for a second, and you can screenshot or whatever it is you like to do as I blabber on, trying to kill some time while you do it. So if you have this scenario, if you have any of these, you are going to do this. And then, you know, you do your thing, right? Properties of logs, L'Hopitals, whatever. Don't forget to exponentiate at the end. That's the killer, right? So if it's multiple choice, there's going to be an option where you don't exponentiate, and that'll be the killer. Don't choose that one. But this is what we did for this one. Shrink it down. This is what we did for this problem. And then this colorful one is what we did for this problem. All right, so I think we're pretty much done with this. Remember, notes 8 is the other place where you will have seen, I guess, in the past, L'Hopital's rule. So go look at that if you're not too sure about it. This is definitely BC level material. It may or may not be on the exam. L'Hopital's for sure is on the exam. Notes 8 type stuff, 100%, no question. But anyway, I'm done with these, so I will see you in the next set of videos, and take care. So see you then.